So our next lesson is factorial notation. So factorials are an easier way, I mentioned this yesterday, to calculate some of those fundamental counting principle instances. So the key idea today is factorial notation is the product of all positive integers from n to 1 shown in math notation using an exclamation mark. Okay, so this is only for positive numbers from whatever we want, as long as it's positive. So it could be 10, it could be 100, it could be 1,000. That would flood your calculator like crazy though, to 1, and we're going to show that with an exclamation mark. So when we get excited in math and we say 4 exclamation mark is the answer, which obviously we all do because we love math, this is actually saying 4 factorial. So we'll talk in a second about what that means. So a baseball coach is determining the batting order for 9 players on the team. How many different orders are possible? Okay, so again, if we thought about this the fundamental counting principle way, like we did yesterday, there would be 9 different spots on the batting order. In the batting order, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the first spot, there's 9 team players to pick from. And then there would be 8 for the next spot because the first guy has already been used. And then 7, and then 6, and then 5, 4, 3, 2. And whoever's last just gets that spot. So if we have to calculator that all out, it takes a little bit, definitely possible, but it takes a few seconds. And we get 362,880. So that's a ton of different combinations, okay? If we want to do this using factorials, this whole thing is what we could write as 9 factorial. So as it said, it's the product of all positive integers from n, so in this case it would be 9, to 1. So this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is 9 factorial, okay? So if we punch this on our calculator, it is going to give us the same result. So we're going to go through how we can do that. So if we press the 9 button because we want 9 factorial, and then we're going to hit math, which is just below the alpha, so right there. And then we're going to scroll over to prob, so that's probability. So this is all probability functions. And then if we scroll down to number 4 or just hit the number 4, we get the factorial, so the exclamation point. So if we do that, we get that 362,880. So same 362,880. Same answer, but definitely a lot easier, okay? So just so you guys don't forget, I want you guys to write the key sequence. So it's going to be math, and then scroll over, scroll over, scroll over, and then it's number 4, okay? So it's within the P, oops, that should be a P, PRB in the math, okay? So in case you ever forget and need to look back on that, that's a good thing to have, okay? So some examples, if we wanted to express 5 factorial times 3 factorial as a product of natural numbers, this is what we could do. So 5 factorial is 5 times 4 times 3 times 2 times 1. And then 3 factorial is 3 times 2 times 1. And so we could either punch all of that in like that, or we could go 5 math, scroll over a few times to get that factorial, and then times math, scroll over, oops, forgot to actually put the 4, so I'm going to insert. I don't know if you guys know the insert function on your calculator, but if you go second delete, right here is insert, so that's getting, the second function is getting insert, and we can actually insert something without having to delete and go back. So 5, oh, it should be a 3. 5 factorial, 3 factorial. Okay, so 720. 720. Okay. Our next example is if we have a factorial divided by another factorial, we can actually simplify. Okay, so if we had 5 factorial divided by 3 factorial, we can write that as 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. Okay, so what's going to happen here is, remember, anytime we have factors, so those are things that are being multiplied, and all of these are that are the same in the top and the bottom of a fraction, we can cancel them. So we can cancel the 3's, the 2's, and the 1's, and we're just left with 5 times 4, which we know is 20. Okay, we could confirm this answer, or this with our calculator. So if I wanted to do 5 factorial divided by 3 factorial, I can confirm that for ourselves. Okay, where this is really important, so let's say, I'll just add another little example in here. If I had 99 factorial divided by 97 factorial, that would flood our calculator screen. Okay, so if I did 99 factorial divided by 97 factorial, even though these calculators are super powerful, it's giving me an overflow error. Okay, so we don't actually get to solve this. So how we could do this is expand stuff out, and we're going to talk about this in a second again, but we could expand this out to 99 times 98 times 97 dot 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 dot, right? And then 97 times 96 times 95 dot 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 dot. Okay, so do you guys see how from 97, I guess I could write a few more in here. So 96 times 95 dot 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 dot. So from 97 onwards, all of these are going to be the same. So the 97s would cancel, the 96s would cancel, the 95s would cancel, and we would just be left with 99 times 98, and that's something that we can very easily put into our calculator and get a number for that's not going to overflow it. Okay, so that's worth knowing how to do. Okay, I'm going to do one more. So 8 factorial 3 factorial divided by 6 factorial 2 factorial. So 8 is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 3 factorial is 3 times, oops, 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And then 2 factorial is 2 times 1. So then we can look at, okay, how many of these can we cancel? So the 6's, the 5's, the 4's, the 3's, the 2's, the 1's, and then the 2, and then the 1. So we just have 8 times 7 times 3. And when we calculate that, we get 168. Okay, so it's handy to know how to expand these things. And I could have just done it 8 times 7 times 6 factorial, because that bit, that's 6, 5, 4, 3, 2, 1, that is 6 factorial, and it could have canceled. So another way we could have done this is 8 times 7 times 6 factorial over 6 factorial, and then multiplied by 3 times 2 factorial divided by 2, oops, 2 factorial. The 6 factorials and the 2 factorials would have canceled, left us with that same thing, so 168. Okay, so either way, whichever one makes more sense to you. This one generally is going to work better for higher numbers, because to write all the digits out, if I give you like 13 or 20 factorial, that would be a pain. Okay, so this time we're kind of doing the opposite. So we want to write each of these in factorial notation. So we want to think about, okay, how we could go from 14 and then 13, 12, 11 and cut off before we get 10. Okay, so if I have 14 factorial divided by, if I multiplied all of this by 10 factorial, which would be the rest of that 14 factorial, but then divided by 10 factorial, those guys would cancel out. So that must have been what would have happened here, right? We would have started with 14 times 13 times 12 times 11 times 10 factorial. If we had divided by 10 factorial, those guys would cancel, and that's what we would be left with. Okay, so if we punch this into our calculator and this into our calculator, we should get the same result. Same deal here. If we start at 9, we must have a 9 factorial in the numerator. And then if we only go till 5, we must have divided by a 4 factorial to get rid of the 4 times 3 times 2 times 1. Okay, we can do this with variables as well. So if we have n factorial divided by n minus 1 factorial, when we're doing it with numbers, expanding and simplifying, we would start to simplify, or we would start to expand out the bigger of the two numbers. So this is n times 1 less than n, so we could represent that as n minus 1 times 2 less than n, and then it just keeps decreasing by 1, dot, dot, dot. And then n minus 1 times n minus 2 times n minus 3, dot, dot, dot. So we could rewrite that, now that we know what a factorial is, we could rewrite that as n times n minus 1 factorial over that n minus 1 factorial that we had. So these two are going to cancel, so we would just be left with n. Okay, same kind of principle here. We want to take whichever number is bigger and start expanding it out. Okay, so a minus 1 would be bigger than a minus 2, right? If it's, let's say a is 10, 9 would be bigger than 8. So we're going to start with a minus 1, and then 1 less than that is a minus 2. And because that matches our bottom, we're going to stop there. And now my a minus 2 factorials match, so I can cancel them out. And I'm just left with a minus 1. The last couple examples, we can use that to actually solve for equations. So if we have n plus 2 factorial, that's n plus 2 times n plus 1, right? 1 less than that times just n times n minus 1, so on and so forth, over n factorial. We know that this is going to be the bigger number. So we can start writing out all of the different numbers that are going to be a part of that. So it's going to be n plus 2 times n plus 1 times n. And again, since n factorial is what we have on the bottom, I'm going to stop at n and make the factorial from there. And that is equal to 42. My n factorials are going to cancel. And so now I'm left with n plus 2 times n plus 1 is equal to 42. To do this, to solve for what n is, we have to factor this, we have to FOIL it out, collect all of our like terms, and then factor again. So it's going to be n times n squared, 2 plus 2n plus n plus 2 equals 42. I need to make this side equal to 0, so I'm going to move it over. N squared plus 3n minus 40 equals to 0. So now I need to factor this. N and n. I need two numbers that multiply to negative 40 and add to positive 3. Okay, so factors of 40, we could use 2 and 20. We could use 1 and 40, but I don't think that's going to work. 4 and 10, 5 and 8. So if I use 5 and 8, I make the 8 a positive and the 5 a negative, then that would work. So what that means is n is equal to negative 8, or n is equal to positive 5, right? Because we're looking for the value of n that makes that whole factor equal to 0. So if we just plugged a 5 in there, that factor would equal 0. Okay, so because we get two solutions, we need to think about, okay, which one works? Remember how we talked about this factorial notation is only for positive integers, so this negative number can't be it, okay? So it can only be a positive solution. Okay, so problems like this are generally you're going to get one positive, one negative. Whatever the negative is not a solution, and the answer just is whatever the positive one is. Okay, same deal here. We have 90 times n minus 4 factorial equals n minus 2 factorial. So we want to take the bigger number and start expanding that. So the 90 and the n minus 4 are going to stay. And then n minus 2 times n minus 3 times n minus 4. And I'm going to stop there because I have a matching factorial on both sides. Okay, so we can think about if I divided both sides by n minus 4 factorial, they would both disappear, so we can cancel them both. So now we have 90 is equal to, I'm going to do my foiling, so n squared minus 3n minus 2n, so negative 5n total, plus 6. Need to move that 90 over, so I subtract it from both sides. So then I end up with negative 84. So again, I need to factor this. I have n and n. I need two numbers that multiply to 84 and add to negative 5. So factors of 84, the ones that I came up with are 7 and 12. Okay, so if I use a negative 12 and a positive 7, that's going to add to my negative 5 and multiply to my negative 84. So what that means is n is equal to 12 and n is equal to negative 7. Again, negative numbers are not valid solutions here. So n being equal to 12 is my accurate number here. Okay, so for practice, read through the pages on this and then do numbers 1, 2 through 10 on page 140. So these ones are pretty small, they're pretty quick. It only takes one page. If you have any questions, let me know.